Hello everyone, and welcome to your second video installment about capacitors. Now, just a quick recap. In our circuits, we can have capacitors that are in series, and we can also have capacitors that are in parallel. Now, capacitors that are in series are connected so that there is only one path for the current to flow through the two capacitors, 2 or 3 or 4 or 19 capacitors. For capacitors to be in parallel, there has to be a sort of junction that the current is going to flow through. So current is going to flow in, split, travel through the two capacitors, and then flow back out. Or think about it like the two capacitors are parallel to each other. Now, we want to define oftentimes the equivalent capacitance in a circuit. And for a series circuit, we had the equivalent capacitance being equal to 1 over C1 plus 1 over C2, on and on, where C1 and C2 were the capacitances of my two capacitors. Over here, for parallel circuits, it's much less complex. The equivalent capacitance is just the sum of the two capacitances. So it would be C1 plus C2. Now, we utilize the fact that in series, capacitors share the same charge. So, each of those capacitors would have a charge Q, whatever that charge was. When capacitors are in parallel, they have the same potential. So the same voltage across each capacitor. And our bread and butter equation was C equals Q over V. Capacitance is charge divided by the voltage across a particular capacitor. And with simple circuits like this, where we either have them in series or we have them in parallel, things are pretty straightforward. But what if I have a circuit that is slightly more complex? So let's say I have a battery and it's linked up to a capacitor, but that capacitor is linked up to two capacitors that are in parallel with each other. So let's say I've got a battery that has a 9-volt potential difference, and I'll call this first capacitor C1, and let's say it's got a capacitance of 1 farad. I'll call this capacitor C2, and I'll say it has a capacitance of 2 farads. And let's say this bottom capacitor C3 also has a capacitance of 1 farad. And my goal is to figure out the charge on each capacitor and the voltage across each capacitor. Okay, so here's what we do. We gradually simplify our circuit down until we get this into just one capacitor. And we start by simplifying the parallel capacitors first. So these two capacitors are parallel with each other. So I can get the equivalent capacitance between capacitors 2 and 3. And that's just going to be the sum of those two capacitors, because remember, the equivalent capacitance when they're in parallel is just the sum. So 2 and 1 gives me an equivalent capacitance of 3 farads. Now, what I've done is I've taken this circuit and I've simplified it down so that I now have two capacitors that are in series with each other. I've got C1 here, and now I've got this C equivalent 2 and 3. And I know that this is 3 farads, and I know that this is 1 farad. So now I'm just dealing with two capacitors that are in series with each other. And I know that when they are in series, the equivalent capacitance is just going to be 1 over C equivalent, which is going to equal 1 over C1 plus 1 over the capacitance here, which is C equivalent of capacitors 2 and 3. Well, 1 over C1 is just going to be 1. So I've got 1 plus 1 over 3. So I'm going to bring this over here. And my C equivalent, now this is for the entire circuit. 1 over C equivalent is going to equal 1 plus 1/3. Well, that's just going to be 4/3. But I have to reciprocate both sides, which means that my equivalent capacitance is equal to 3/4 of a farad. So I've basically gotten the circuit down to just one capacitor. Okay? And it has a capacitance of the C equivalent, which is 3/4 of a farad. So now, where do we go from here? Well, I know the equivalent capacitance of here. So I'm going to draw this a little bit bigger so that we can get a good idea of what's going on. I've got my 9-volt battery, and then I've got my equivalent capacitance, which is, remember, a combination of all my other capacitors. And it was 3/4 of a farad. Well, if we utilize the loop rule, and I start down here, I come across this 9-volt, this negative 9-volt terminal. The loop rule says if I make it all the way around, then I need to end up with no voltage. So I first hit -9, then I go around, and I hit the positive side of my capacitor. So I hit the positive voltage of that capacitor. I don't know what it is, but I know it has some voltage. I'll just call it VC. Well, then I end up back where I start, which means it equals 0, which means the voltage across my equivalent capacitor is 9 volts. So what I can do now is I can figure out the charge on my equivalent capacitor. So C equivalent equals Q over VC, the charge on my capacitor. I know that C equivalent is 3/4, and I know that my voltage is 9. Multiply both sides by 9, and I get a charge of 9 times 3, 27 over 4 coulombs. So that's the charge on my equivalent capacitor. But remember, my equivalent capacitor was those two capacitors in series, my C1 and C equivalent of 2 and 3, which means that anything in series has the same charge. In other words, C1 has a charge of 27 over 4 coulombs, and C equivalent of 2 and 3 has a charge of 2 coulombs, or 27 over 4 coulombs. So what we're going to do, the process, you simplify the circuit, and then you gradually build on it back to where you started. So my C equivalent was, that looks horrible. My C equivalent was C1 plus in series with C equivalent of 2 and 3. Okay, and C1 had 1 farad, and then C equivalent between 2 and 3 had a capacitance of 3 farads. But now I know that they both have a charge of 27 over 4 coulombs. Well, now I know the capacitance and I know the charge. I can solve for the voltage across each of those. Because remember, in series they will have the same charge, in parallel they will have the same voltage. So let's look at C1. C1 equals Q over V1. Now, Q, we've already figured it's 27 over 4. Now, divided by V1, which is like multiplying by 1 over V1. And remember, C1, the capacitance, is 1. So this equals 1. Well, basically, I've got to cancel everything out. So I can multiply both sides by V1 to give me a voltage drop of 27 over 4 volts across that capacitor. Now, to check and make sure that I'm correct, I can figure out the voltage across this capacitor, but I know that the voltage here plus the voltage here need to give me 9 because of the loop rule. So let's look at the voltage across this capacitor. C equivalent of 2 and 3 was 3. Well, 3 is going to equal Q over V, the voltage across that. We can call that V23, the voltage across that capacitor. I know Q, it's 27 over 4. So I'm going to bring this work over here. 3 equals 27 over 4 times 1 over V23. So now I can multiply both sides by V23, divide both sides by 3, to give me the voltage across that capacitor being equal to 27 over, 3 times 4 is 12 volts. And if 27 divided by 12 plus 27 divided by 4, look at that, it gives me 9. So we're all good. And I have found the voltage across that first capacitor, and I've found the charge on that first capacitor. So C1 is all taken care of. I still have to dive further in and look at the two capacitors that were in parallel with each other. So let's look at what we know about those capacitors. I know the voltage across their equivalent capacitor. It's 27 over 12. And remember, C equivalent was those two capacitors in parallel. Things in parallel have the same voltage, which means the voltage across my second capacitor and the voltage across my third capacitor both equal 27 over 12 volts. Well, I knew the capacitance of oh wow, excuse me. Oh, I'm okay. I knew the capacitance of C2, it was 2 farads, and I knew the capacitance of the third capacitor, it was 1 farad. Well, now I can use C2 equals Q2 over V2, and C3 equals Q3 over V3. So you start and get the capacitor down to just 1. Then you work backwards out, looking at what's in series and looking at what's in parallel. That's how you attack capacitor circuit problems.